Buenos días a todos los que están conectándose y a todos los que, pues, por supuesto, están en nuestro panel de speakers el día de hoy. Quiero abrir este evento dándole las gracias principalmente a Synertic, que con ellos logramos hacer este webinar y nos han apoyado en todo el tema de divulgación. Synertic es la asociación Alianza Synertic y está a cargo de crear alianzas entre empresas de TI y software. Así que, pues en primer lugar, gracias a ellos por apoyarnos en este evento que estamos llevando a cabo. Y en segundo lugar pues darle gracias a nuestros panelistas que están acá y nos van a hablar hoy acerca de computación cuántica. Así que para cumplir con el horario, le doy la bienvenida a Óscar Garavito. Óscar Garavito es el director de nuestra área de inteligencia artificial y de nuestro laboratorio de inteligencia artificial llamado Equinox. Hola, Óscar, ¿cómo estás?
Hola, Juli, muy buenos días. Bueno, muchísimas gracias a todos. Muchas gracias por acompañarnos en este nuevo evento. Queremos agradecer, pues, digamos, a Synertic, como decía Juli, por toda la difusión del evento. Muchísimas gracias. Como bien decía Juli, somos Equinox AI Lab. Nosotros somos el laboratorio de inteligencia artificial de este software. Y pues dentro de Equinox venimos trabajando en algunas iniciativas ya, pues digamos, a nivel estratégico que involucran varios temas que les vamos a contar un poquito. Bueno, digamos que uno de los temas que a nosotros nos interesa mucho es el desarrollo de productos. Dentro de eso, pues tenemos Numerate, que es una aplicación que nos permite contar objetos a través del uso de análisis de imágenes de Computer Vision. Tenemos también otro producto que se llama QuickBot, con el cual pues ayudamos a las organizaciones a utilizar agentes, asistentes digitales para pues digamos varios escenarios de negocio. Eso es lo que tenemos relacionado con temas de producto. Tenemos también una parte de servicios. En la parte de servicios pues ofrecemos diferentes opciones para las compañías para hacer temas de consultoría en inteligencia artificial. Tenemos una metodología propia que nos permite a nosotros, pues, digamos, guiar a las compañías en este proceso de integrar inteligencia artificial a su negocio. Y pues en la última parte, el último frente que tenemos es toda la parte de investigación y desarrollo, pues que, digamos, aquí traemos este evento tan bonito llamado Navegando la computación cuántica, que hace parte, pues, digamos, de este frente que es investigación y desarrollo. Queríamos, pues, tener como un abrebocas sobre uno de estos temas, pues, tan interesantes. Esto realmente, pues, se viene ya formando como una nueva revolución tecnológica en la cual, pues, va a tocar todas las empresas, va a cambiar la forma en la que hacemos las cosas, van realmente a impactar mucho los negocios, porque pues es una tecnología que pues realmente va a hacer que las cosas sean mucho más aceleradas. Tenemos algunos escenarios que queremos que ustedes entiendan para pues que vean cuál va a ser el potencial y todo lo que se viene hacia pues un par de años. Nosotros ya pues queremos tener un pie, digamos, en el futuro y por eso nos interesa empezar a trabajar con estos nuevos temas, con estas nuevas tendencias y pues sobre todo pues estar a la vanguardia tecnológica como siempre lo ha hecho hace software. Bueno, como parte del día quiero presentarles a nuestro speaker principal. Él es Thomas Clark, él es nuestro AI intern, él está ubicado en Londres. Pues digamos que venimos trabajando con él ya hace un par de meses. Él es físico de profesión, ¿sí? Él pues, es físico de King College de London. Se graduó con honores, es una persona muy inteligente. Actualmente es estudiante de la maestría de Quantum Technology en University College of London. Realmente es una persona muy apasionada por todos estos temas de la mecánica cuántica. Cuando empezó a estudiar física, se enamoró de la mecánica cuántica, no solamente de la parte fundamental, digamos, del conocimiento base, sino también de cómo se puede empezar a aplicar esto en problemas de la vida real, digamos, en escenarios ya de negocio, cómo se pueden generar nuevas tecnologías y nuevos temas alrededor de todo lo que tiene que ver con la computación cuántica. Y pues en particular le interesa mucho todos los temas relacionados con la construcción de los computadores cuánticos, que es un tema bastante interesante. Digamos, hay muchos retos, hay muchas barreras para lograr construir este tipo de computadores. Entonces, pues le doy la bienvenida a un gran compañero y a un gran speaker como es Thomas. Hola Thomas, bienvenido.
Well, that was good. Gracias. Thank you for your kind introduction, and thank you to everyone who's given me this opportunity to speak to you, and for everyone here who has taken time out of their day for my talk. It will be in English, and I hope you enjoy it. And vale. Empezamos. Yeah. Can my screen? Okay, there we go. So this talk will be on quantum computing. I will be giving an overview and a business introduction. So what that means specifically is I will be covering what is quantum computing, what the current state of the industry is, what quantum computing means for businesses, so that's the applications, and I'll be offering some practical advice if you're considering investigating quantum computing. So to begin with, I will introduce how normal computing works. So this is the computers that are in your phone or in your how you're watching this webinar. And the basic principle is they take an input, say the number 2, they perform an algorithm, which could be multiplying by 3, and then they get an output, which would be 6. And I know you might be thinking, well, there are von Neumann architectures and there's a lot of more complicated stuff, but yes, on this very simple model, that's how computers work. And this has been true for almost 200 years, with the first computer being invented by Charles Babbage and built in 1822, all the way to the supercomputers of today. So this is the IBM Summit, which I will be referring to a bit. So computers are really good at a lot of things. They can read emails, they can do webinars, they can do searches on Google, but there are some problems that computers struggle with. And one of those is simulating nature. So this thing right here is the protein for COVID-19. And to simulate this on a normal computer, even on a supercomputer, is very difficult. And the reason for this is that you have to build a model with a lot of different parameters. So in this case, you needed more than 442,000 atoms. And it's not just the number of atoms, but the precision that is required in building such a simulation would generate hundreds of billions of data points within a microsecond. And that's a lot of data and a lot of computational work. So the way this was done last year is it was tackled using distributed computing. So distributed computing relies on using a great many computers all over the world to share their computing resources to do protein folding. And this had 700,000 contributors, including this computer that I'm using now to do the presentation. And it had a total computational power greater than 7 times the computing power of the most powerful supercomputer, which I think was the IBM Summit at the time. So that's a lot of computing power, and it's a very important problem. And the reason this was difficult to do is because there are so many different ways you can have a protein to be folded. But a classical computer has to go through a large number of them to get to the optimal result. And this is where quantum computing is different. So before you had a single input and a single output, but with a quantum computer, you can take many inputs. In fact, you could take all possible inputs, and you could act on all of them at once using a quantum algorithm. And then that in turn generates all possible outputs. And from that, you can extract a particular output. So for instance, with the protein folding, you could take all the possible configurations of your COVID-19, you could operate on all of them, and then you could get a particular result, which would hopefully be a better configuration. And what a quantum computer looks like, this is typically what they resemble. This is what Google's quantum computer looks like at the moment. And it looks closer to Babbage's difference engine. That is the Victorian device with all the cogs than the supercomputers of today. So there is still a long way to go. And so to understand quantum computing, you need to understand a bit about qubits. And instead of going into quantum mechanics, I'm going to use this example of a spinning coin. So if you have a coin that's spinning, you cannot say the coin is a head or a tail, because that doesn't really make sense. It's kind of neither and both. So we say that the spinning coin is a combination of both the head and the tail. So this is the UK currency. You have the queen there on the coin. And qubits can be in the state 0 and 1 at the same time. So your binary bit is either 0 or 1, and your qubit can be both. But there's a nice property about qubits, which is that because they can be both, if you add another qubit, suddenly it's not just a head and a tail. You have 2 qubits. So you have 4 possible states it can be in. If you have 2 coins, they can be head, head, tail, tail, head, tail, or tail, head. And as you add more and more coins that you're spinning, there are more and more possible combinations. So each time you add a coin, you double the number of possible combinations you can have. And what this ends up with is very quickly you can get very large numbers of possible combinations. And then when these coins land, we say in terms of quantum computing, we describe this as a measurement. You get either a head or a tail. So in the case of our qubit, we get a 0 or a 1. And if you have n qubits, there are 2 to the n possible states. And 2 to the n is quite a large number, because the IBM Hummingbird, which is the quantum computer they have, this slide is going to become out of date very quickly, which has only 65 qubits, would require 4.2 million terabytes of RAM to store the state of that. So you think about your computer, which might have a terabyte on it, which would be a very large amount of storage. You think about 4.2 million of those. That is very difficult to store that kind of information. And this is very good because there are many problems where there are exponentially many possible solutions. So this 2 to the n becomes quite useful. And this is a very simple application of what you could do with a quantum computer. And this is using a quantum computer to generate random numbers. Now, random numbers are important for cybersecurity. Many encryption schemes are based on generating random keys. And quantum computers can generate perfectly random numbers. And what I'm going to show you is a very simple example of a quantum algorithm. So what you're looking at here is on the top right, this is what a quantum circuit looks like. So this is how we visualize a quantum algorithm. And here on the left, you have all these qubits. So these are like your coins. And then we have this thing in a square, which is an H. So that's spinning the coin. And then the coin lands and you look at the result. So this corresponds to a measurement. And then you save whatever the number is in here. So that's how basic quantum algorithms work. And what we're doing here is we're spinning our coin many times, or we're spinning many coins many times, and using that to generate random numbers. So you can see we get 7, 3, 6. And to check that it's doing its job properly, we can plot a histogram and verify that there's randomness. It's not the most rigorous statistical test, but it's good enough. And you can see here that this code is written in Python, which is true for many quantum computing schemes. So random numbers are nice, but if you want to simulate say COVID-19, you're not going to want to do it just by using random numbers. And so there's another phenomena. So this is a quantum effect, which is called interference. And interference is very useful because if we want to get a good solution, we want that solution to come out most of the time. And so you can see in this quantum circuit, we take our coin, we flip it, and usually if you were to flip a coin and then flip it again, that would be the same as flipping it once, because it's 50-50 chance and then a 50-50 chance again. So you would expect to get a 50-50 distribution here. But actually that's not what we get, because with interference, you cancel out the other states. So in this case, we measure 0 almost all of the time. And this is very important. The next feature of quantum computing is it takes advantage of something called entanglement. And this is a sort of complicated physical concept to explain. But using the coin analogy, you can imagine if you have 2 coins and you flip both of your coins. And usually when you do this, the coins don't affect each other. But what if you notice that each time you flipped one of the coin, say you get a head, on the other coin, you always get a tail. Or if on the first coin you got a tail and on the second coin you got a head, then you would notice that there's something going on with these coins, because they always come in these opposite pairs. And with qubits, we can do this. So we say there are very strong correlations between them. And you can go even further and say that one of the qubits controls the state of the other one. And for those of you who know a little bit about programming, there's these important if statements that allow you to do certain logic. And this is kind of similar to what we have here. But in the quantum case, it's even better because you can preserve the superposition. So the superposition is when you have all the possible combinations. And what this means is that your quantum computer cannot be described by each qubit on its own, whereas with binary, you can describe a binary state as the sum of its parts. So that's nice, but why do we want to use these phenomena? What advantages do they give? Well, it turns out that quantum computing can expand the range of problems that we can solve with computers. So what we can do is we can write quantum algorithms that enable us to solve problems that previously couldn't be solved before. So if we have here in P space all the possible problems we can solve, or not necessarily we can solve, all the possible problems we can have, there are these problems here called P problems, for which we can solve pretty well on computers. So for instance, addition, easy. You can add numbers as big as you like. But then there are other problems, such as factorizing large products of prime numbers that are difficult to do. And quantum computers expand this range into what's called BQP. And so the consequence of that is that there are certain problems where finding a solution is much, much easier on a quantum algorithm. And of course, if I'm going to talk about quantum algorithms, I have to mention Schulz algorithm, which is perhaps the most famous quantum algorithm. And the significance of this is that not all, but the most popular encryption method is based on how difficult it is to factorize the product of prime numbers. So if you have a look over here, you can see this RSA key, and here is a number. And this number, 449,054, is the product of 2 prime numbers. So you can multiply 2 prime numbers together to make this number. But it's very difficult, if given this number, to find the 2 numbers that were multiplied together. And that's what encryption is based on. So with Schulz algorithm, you can actually break this and you can find the 2 numbers. And Schulz algorithm is particularly exciting because it scales exponentially faster than the classical approach. And what do I mean by exponentially? Well, if we have a look here, you can compare how long it would take to solve, to factorize this number on a quantum machine and a classical machine. So on the quantum machine, you have the blue curve. And on the y-axis, you can see how long it takes to solve. So for instance, let's say this could be seconds. And on the x-axis, you have the size of the problem, which could be the number of digits in the number you're trying to factorize. You see that at some point here, which is around, say, 45, the quantum factorization becomes faster than the classical factorization. And as the number becomes bigger and bigger, the gap by which the quantum machine is faster increases. So you can see here, if we had, say, 80 digits, then our quantum computer could, let's say, do it in 1 million seconds, but our classical device would require 10 to the 12, which would be about a pettasecond or 1,000 billion seconds. So you would have a speed up of about 1 million times, which is pretty huge. So that's a little bit about quantum algorithms and what quantum computing is. But quantum, or rather, the RSA encryption isn't about to be broken just yet. So we have to discuss what the current state of quantum computers are to put this into context. So quantum computing can be described in 3 phases, or kind of 3 eras. So if we have a look at this chart here, which was made by Amazon Web Services, you can see this region 1. This is when you have quantum computers that are small. So by that, they have few qubits. It's a low quantity, and of a low quality. So they have very high error rates. So these computers, you could simulate them on a machine. So you can write some code on a classical computer and simulate the quantum computer easily. That's not particularly great. But if you had a quantum computer that's bigger and has better quality, it can no longer be simulated on a normal computer. So we call this the NISQ era, or noisy intermediate scale quantum, where it cannot be simulated classically, but it is small and unreliable still. And then moving on, this is the era that we really want to be in, this 3 region here. And this is where we have what we call full-scale fault-tolerant quantum computing. So you can think of that as having really powerful quantum computers that are really good and can implement all the quantum algorithms you want. And to get to that point, you need to have on the order of hundreds of thousands of qubits that are of much better quality of what we have today. So today, we're somewhere about here, which is still a ways to go. There are a few more things to say about how you can describe quantum computing, and that is quantum advantage. So quantum advantage occurs when you have a quantum computer that is faster or can produce better results than the most accurate and the most powerful supercomputer. Then you have quantum supremacy, where you have a quantum computer that can carry out a computation that the most powerful supercomputer cannot do in a reasonable amount of time. So, for example, if you had a quantum computer that could solve a problem in a week, whereas your supercomputer on the best algorithm would take 100 years, then you would say you have quantum supremacy. And finally, quantum as a service. So typically with quantum computing, you might think that you have to buy one of these machines. So like the one I showed you earlier that Google has. And you think, oh, you're going to need this whole room for it. You're going to need all these engineers to make sure it's okay. But thankfully, that's not the way quantum computing is going. So with cloud computing, you can access a quantum computer over the internet at significantly lower cost than if you needed to buy one yourself. So to do quantum computing, all you need is a good internet connection. And that makes life a lot better. So there are a few different ways you can build a quantum computer. And there are hardware providers that build quantum computers differently. So the most common approach, or at least the one which gets the most press, is the superconducting approach that Google and IBM employ. And the superconducting approach builds these circuits, they're called Josephson junctions, that are cooled to almost absolute zero. And at the moment, the highest number of qubits that they've managed to achieve is 72. There are other approaches. So one that's lesser known is built on trapped ions. So if you were to take an atom and knock out some of the electrons, you could make it into an ion, and then you put it into a trap, and you can control the atom in that trap in order to carry out computations. This approach has its own advantages and disadvantages. Then there's the photonic approach, where you send light through a circuit and you can measure the output in a certain way. You can do computations on that. And then there's D-Wave. So D-Wave have what they call a quantum annealer, which is a very interesting device because it fundamentally operates differently to all the other quantum computers. And you'll notice that they have 5,000 qubits, which looks quite a lot better than the rest of them, but it comes with the important caveat that you cannot perform universal operations. So you can't do all the quantum algorithms. You can only do a specific type of problem, but a very important problem. And there are many other approaches that other companies are pursuing, including Microsoft and Intel. So it turns out that there are a lot of different ways you can write a quantum algorithm. And for those of you who are familiar with Python, you're going to be happy about this because what you see here, these are a bunch of libraries for quantum computing. They are all based on Python. So these are the number of downloads in the 30 days to June this year. And all of them have learning resources freely available. So you can go on the internet and you can search for this platform name and you can find instructions. Some of these are open source, so that's good. And Microsoft have their own dedicated quantum programming language called Q#. Okay, so that's what quantum computing is. But what does it mean for business? So how does everything that I say translate into value? And how can you make sense of all the hype? Well, if we take a look at an optimistic perspective, this is an analysis done by Boston Consultancy Group. So you can see here, they have come up with a few categories: cryptography, optimization, machine learning, and simulation. And for each of those areas, they have different applications and an associated value creation potential. So this is, if you were to build a quantum computer in the full-scale fault-tolerant, a really big, high-quality quantum computer, what kind of value do they predict it could bring to industry? And they range from about, so $0 to $10 billion on the low end to $100 billion on the high end. So this is potentially quite a high value market. And on the right, I've just taken, this is straight from the ASA software website. You can see lots of different industries in which they operate and how they can be impacted by these applications. So for instance, in finance, you see that portfolio optimization could generate between 20 and $50 billion of value. And so I'm going to go and discuss in greater depth a few of these applications. I'll be focusing on chemistry. So that's to do with problems facing pharmaceuticals, drug development, material science. I'll be talking about supply chains and optimization. And finally, I will be talking about something else. So, quantum simulation. There's an important quote by Richard Feynman that says, if you want to simulate nature, you'd better make your simulation quantum. And this is, well, a reason why we should build quantum computers. So as we saw with the protein chains of the COVID-19, modeling complex chemicals is difficult. And in the case of chemistry, this is hard because they are inherently quantum systems. So to make a simulation of a quantum system, we make some classical approximations. And sometimes these fall a bit short. So if you're trying to develop a material and your simulations aren't good enough, sometimes you just have to make the material yourself, try it a bunch of times. And this is a very wasteful and time-intensive process. If we could create a quantum simulation that would be a more accurate simulation, we could remove the need to generate this, to create the substance itself. And an example of how this could be potentially quite lucrative is in pharmaceuticals. So if you want to model how a drug undergoes a chemical reaction, that's a very important thing to know. If you're developing a drug, you need it to work, and you want to make sure it doesn't have bad side effects. But there is a limit to how well you can computationally simulate these things. So what ends up happening is that the drug has to be chemically synthesized and undergo long and expensive clinical trials. And this is expensive because you don't try this once to get a drug. You have to try it many, many times. And there's a very high failure rate at the late stages. So the drug goes through all these different trials and then fails at the end, which means you spent a lot of money and a lot of time developing something that doesn't work. And this is particularly significant because 20% of global research and development spending is on pharmaceuticals. So even if quantum computing could only provide perhaps a 1% or a 10% reduction in development times, that could translate into value in the billions. And Bayer, amongst many others, are investigating how this can be done. So the next application that I'll be talking about is route optimization. So there is a class of problems that are known as the traveling salesman problem. And the traveling salesman problem is that if you have a list of places, you want to find the shortest route going through each of these places only once. So you see here on the left, you have a map of the US. So if you want to go through a bunch of cities in the US, you might want to find the shortest path that goes through each of them. And the reason this is difficult is because even with a small number of places, there are a large number of possible routes. So for 10 places, there are more than 36,000 possible routes. That's still easy to compute. But for 50 places, there are now 6 times 10 to the 62 possible combinations, which is a very huge number. But in the real world, we don't have this idealized map. We have constraints. So for instance, if you are shipping goods, you might have the restriction that ships have to arrive at particular times. And this can make the problem harder and more difficult to solve. And in addition to this, you have volatile real-world conditions. So for instance, this year, the Ever Given cargo ship got stuck in the Suez Canal, which meant a lot of ships had to find new routes, and this can cause quite a lot of disruption. And the good thing about these types of problems is this isn't just an area where quantum computing might be useful. There's been a pilot study done by D-Wave in partnership with Volkswagen, and they've actually developed a little project to test this out. So what you're looking at here on the left, this is a map of Barcelona, and this is the OneWeb Summit in 2019. And what they did is they used an approach where they generated a lot of routes for their buses. So you can see they want to get from this point to the conference over here. And they wanted to optimize these routes in real time. So what they did is they took live traffic data, and they were able to update the routes of the buses in real time with an Android app that the driver interfaced with. So they did 185 trips for 9 buses with updates every 120 seconds. So what you can learn from this is something which is actually usable. It's practical. Although this is a very small test case example, it shows that quantum computing does work. And if you want to know more about this, I recommend you take a look at this paper over here. It's quite good. And this kind of problem is not unique just to optimizing bus routes, but you can apply it to air traffic control, supply chain optimization, warehouse fulfillment, and last mile delivery. So this is important for lots of different businesses in lots of different areas where they want to move things quickly. Another application is in finance. So this is an area where a lot of work has been done to investigate how quantum computing can impact finance. And specifically, I'll be looking into portfolio optimization. So a portfolio is a combination of stocks, and each stock has associated return and a risk. And typically what a bank would like to do is they would like to maximize the portfolio for a given amount of risk. So from a large pool of portfolio options, they want to choose a set of stocks that will give them the best combination of returns and risk. And what this requires is you have to make a simulation, you have to make a model, and you have to predict what the returns of the stocks are going to be. And the way this is done is using Monte Carlo simulations, which is a very ubiquitous method in lots of areas. And because these calculations are very difficult, it can sometimes take 12 to 24 hours to process. On the other hand, quantum Monte Carlo is an approach that leverages quantum computing to bring down the time it would take to run the simulation. And in theory, if this can be done, it could produce a quadratic speedup. So what I mean by a quadratic speedup is if it were to take 1 million seconds on a traditional Monte Carlo algorithm, a quadratic speedup would bring it down to 1,000 seconds. So that can be quite significant. And it could mean you could do your computation from taking overnight to just a few hours. However, in order to achieve this, we would need to really build much more powerful quantum computers. The quantum computers we have today and in the next few years is not going to be able to tackle this problem. And similarly, it's not just portfolio optimization, but you could do asset pricing, you could do risk analysis, you could do fraud detection, and you could, in principle, do market predictions. I recommend, if you're interested in hearing more about this, you can check out Multiverse Computing, who specialize in quantum computing for the financial industry. So when you are looking at quantum computing and you're looking at these applications, there's a good guide, this is from Rolls-Royce, to assessing how mature the solution is. And we call this quantum application readiness level. So what you're looking at here is a project that can be described as basic research. And that is someone is proposing a quantum algorithm, but perhaps hasn't tested it or hasn't really done anything with it. And then at the best stage, they've developed it and tested that it works. Then there's industrialization. So this is where you build a working prototype and show that it can work and go on to develop it in a more realistic environment. on industry scale problems. And then finally, we have industrial application. So that's where a quantum solution is being used in industry at scale. And for context, my quantum random number generator is a proof of concept, which works, but is hardly industry scale. Whereas the Volkswagen bus routing would be a number 5. So it's a working prototype that's interfaced with classical code. So if you've heard this stuff and you're thinking, okay, this seems quite interesting, how can I incorporate it into what I do? How can it add value to what I'm working on? Well, this is where having a business strategy is useful. And this is the strategy that I'm proposing. So the first thing to do is to analyze your workflow problem and find the part with the greatest computational cost. So for instance, if you're doing an artificial intelligence project, you might have a neural network that is very expensive to train. So training your neural network could be the most expensive computational cost. Then you can research whether or not a quantum solution has been proposed for that problem. So has somebody come up with a quantum algorithm that could make your computationally expensive process easier to solve? These two parts, not too difficult. The next part is difficult. So then you need to designate or hire dedicated quantum research staff who are familiar with the problem. So this requires two things. The first thing is they need to be able to do quantum computing. And the second part is they need to know the problem, because you can have academic physics PhDs who are really good at quantum computing, but don't have a clue how to solve your specific problem. Or you can have people who are really good at solving your problem in the current way, but can't leverage quantum solutions. The next part is to partner with established quantum computing hardware and software providers to develop a small test prototype. So for instance, Volkswagen have been working with D-Wave for 6 years, and they've collaborated a lot. The next part, you could also, for instance, go with Google or IBM, are also offering partnerships, is to evaluate the success of the prototype and extrapolate scalability to industrial problem size. So, for instance, with the bus routing, you can evaluate how successful it can be, and then you can say, well, if I wanted to deploy this at scale, what would I require? And the next part is also difficult, is to be flexible. So quantum computing is a rapidly evolving field. It's changing all the time. And the research community are constantly creating new algorithms, new approaches. And so if you build a quantum solution, you're going to need to refine it and update it all the time. And the last part is to monitor the state of the industry and scale over time. So if you've extrapolated and say, well, for this to be practical, we need 10,000 qubits, then you're going to want to monitor the state of the industry and see how long it's going to take to get to those 10,000 qubits. And this is a strategy that you could use. Some advice for implementing this strategy. Not all businesses are going to need quantum computing. So the second point, research whether quantum solutions have been proposed, doesn't necessarily mean those solutions will work for you. For instance, if you recognize that your database is a problem because it stores a lot of information, then you're not going to have a quantum computer that can build a database. It's not particularly feasible. So not all businesses will need quantum computing. The next part is that quantum computing has quite a steep learning curve. So although it is possible to learn quantum computing, it does take time. Patience is key. And what I mean by that is if you look at the industrial prototypes, these are being done by companies who have a large amount of money and a large amount of time. Volkswagen isn't going anywhere. And similarly, if JP Morgan wanted to do a quantum project, they don't mind waiting 10 years and spending $10 million on it because they're going to be there for a while and they can invest in the long term. So don't go developing a project and thinking you're going to have results immediately, because that's not realistic in most cases. The next part is a bit more speculative. So the opportunity cost, or the first mover advantage, can be significant if an industry is disrupted by quantum computing. So for instance, if you're in finance and you're able to solve to run a computation in hours when it would have taken a whole day, that can be hugely disruptive. And if everyone else does it before you do it, then that's going to be problematic, because it's going to take you a long time to get the quantum workforce to adapt to quantum and integrate it into your business. And that could be quite difficult. But on the flip side of that, don't explore quantum simply because of a fear of missing out. So this is called FOMO. So don't just do it because it's cool or because you want to have quantum in the name, even if that doesn't really translate into any actual business advantage. And in light of that, I'm going to mention a few things about perspectives on quantum computing. So academics are much more cautious than industry about the state of quantum computing. So if you listen to people at universities versus people in quantum computing companies, you might hear different things, particularly when it comes to the field of quantum machine learning. And another thing is that putting quantum in front doesn't necessarily mean better. So for instance, there are cases where a quantum speed up is theoretically possible, but practically it cancels out because of other factors. So it doesn't necessarily mean, quantum doesn't mean better, and certainly not for everything. The third point is that artificial intelligence or machine learning is already very good for many of these problems and is increasingly showing promise and is a rapidly developing field. So the bar for a quantum computer, that is what a quantum computer needs to surpass to add value, is constantly pushing forwards. And then quantum advantage exists in principle. We can write algorithms that are theoretically faster, but it actually has to be done with projects. So that's something that I would look out for when assessing quantum computing. Some additional thoughts. Quantum computing is a dynamic and exciting field, and better quantum algorithms are emerging all the time. For instance, I've talked about quantum Monte Carlo, but there are other approaches that could be used, and they all have their own advantages and disadvantages. You don't need quantum mechanics to do quantum computing. So this might come as a surprise, but you can actually, if you're going to be using a quantum algorithm that somebody else has written, and you're just going to be tuning it and using it, then you don't need to have quantum mechanics to use quantum computing. You don't need to have electronic engineering to use a computer or be a computer scientist. That said, if you are developing a quantum computing solution, it can be highly academic and theoretical. Certainly at the moment, many of the papers that are coming out in quantum computing are coming out in physics journals, which says a lot. And the people who are publishing these results, in the majority of cases, work at universities. So this is still a very theoretical field at the moment. And the field is an early stage. So the quantum computers at the moment are still a long way from maturity. Now, you might have listened to this talk and thought, oh, this sounds quite interesting. I'd like to hear more. I'd like to know more about the technical details, or I might like to know more about a particular application or a use case. And there are lots of ways you can learn more about this. So IBM have created what they call the Qiskit textbook. That's this thing over here. It is brilliant. And you can learn all about quantum computing, how to write algorithms, how to test them. D-Wave have Leap, which is a similar approach, and they have some demos. They let you access their quantum computers on the cloud for a very limited amount of time. But you can, if you want to play around with quantum computing, you can actually access IBM and D-Wave's resources for free, which is pretty nice. There are lots of online courses available. There are specific newsletters that are dedicated just for quantum computing. So the quantum computing report is quite good, and so is the Quantum Daily. There's the archive for those of you who like reading academic papers. And there are lots of conferences and events. So recently there was the Quantum Computing Summit. And this year, there was an event called Quantum Latino, which is an event that aims to build a quantum community in South America. So if you'd like to hear quantum computing but in Spanish, I recommend you go on YouTube and type in Quantum Latino, because they have a lot of really great resources over there. So that concludes my presentation. I would again like to say thank you all for watching. Thank you for your attention. And thank you again for giving me this opportunity to give this presentation.
Muchas gracias a ti, Thomas, por esta intervención. It was wonderful. I learned a lot. Now we are going to read some questions. I'm going to read the questions and then Oscar is going to translate the answer. Tenemos preguntas en inglés y en español, entonces, bueno, vamos a empezar con algunas de las preguntas que tenemos. Van a ir saliendo acá en pantalla, pues para que ustedes sepan. En ese momento tenemos bastantes preguntas. No creo que las alcancemos a responder todas, pues en el tiempo que nos quedan, pero vamos a empezar con la primera, que es de Jonathan. Si me ayudan, por favor, a ponerla acá en pantalla. Jonathan nos pregunta, a ver, un momento que no me la han enviado. Ahí está. What are the biggest technical barriers facing quantum computers?
So, as we saw earlier, there are lots of different ways you can build a quantum computer. And each way that you build a quantum computer has its advantages and its limitations. So for instance, in the superconducting approach that Google have used, they can make very fast qubits, but they're limited because they have what we call short decoherence times. So the qubit only exists for so long, which limits how many computations you can carry out with it before it decoheres. Other approaches have other problems. So the trapped ion approach, which is quite popular, is quite slow. And so they are more difficult to work with. But I will mention this, we take for granted how speedy and reliable our normal computers are, but they've had a 60-year head start. And if you look at how reliable computing was in the 40s, it certainly wasn't as good as it is today. And with industries and academics around the world working on this, there are many different ways to solve these problems that people are working on.
Ok, gracias, Tomás. Básicamente las limitantes o las barreras que afronta la computación cuántica están un poco relacionadas con la construcción de las máquinas como tal, los computadores cuánticos. Como nos mostró Tomás, en una parte de las aproximaciones, la que utiliza Google, ellos necesitan que pues digamos que los qubits se enfríen cerca del cero absoluto. Entonces, pues básicamente solo pueden utilizarse durante un tiempo definido, porque después de esto empiezan a generarse un poco de errores. Con la otra aproximación de los iones atrapados, pues aquí el problema es que se tienen pues tiempos un poco muy lentos, pues un poco más lentos. Entonces, digamos que son como las principales barreras que se tienen en términos ya de utilización de computación cuántica. Claramente, pues tenemos que alcanzar un nivel de madurez, como se hizo, pues, digamos, en la computación clásica, que lleva una evolución, pues, alrededor de 60 años de ventaja. Y, pues, actualmente la industria, la academia, están trabajando en primera línea para resolver y mitigar este tipo de problemas que, pues, afronta la computación cuántica.
Listo, gracias. Tenemos por acá otra pregunta que nos la hace Miguel Cuadros y él nos está preguntando, ¿is quantum computing a threat to the blockchain? Yo no sé si perdón que te pare, pero I think you could I don't know, answer a sentence and then Oscar translate it.
Okay.
Maybe it's easier for the public.
Okay.
Thanks.
Yeah, sorry about that. So this is a difficult question to answer because there isn't one sort of blockchain technology, and to be honest, I don't really know. I think if it were to be a threat, it would have to be a significantly more powerful quantum computer. And I would also argue that in principle, you could simply change your method of encryption to make it quantum resistant. So I would say probably not.
Ok, bueno, dice Thomas que, pues, que no está tan seguro de cómo puede ser una amenaza para el blockchain. Pues claramente aquí hay pues varios factores a evaluar. Pues digamos que con la parte de la encripción, que es pues digamos uno de los temas que se pueden potenciar con la computación cuántica, pues digamos que se podrían tener algunas cambios significativos, pero pues realmente no se tiene certeza en este momento de cómo la podría afectar.
Perfecto, tengo entendido, o bueno, hablábamos, los invito a todos a ver por ahí por redes, tenemos otra persona experta en temas de computación cuántica, y hace poquito lanzamos como una entrevista que le hicimos acerca de estos temas, y él ahí habla un poco acerca de todo este tema de la seguridad que van a tener, o que se va a tener que tener, valga la redundancia, en un futuro cuando los computadores cuánticos estén, pues digamos, bien posicionados, porque para ellos va a ser más fácil descifrar todo este tema. Entonces, la información sí va a tener que jugar un papel, o sea, el blockchain va a tener que jugar un papel importante en el tema de cómo se encripta esa información, sobre todo para temas de seguridad. Entonces ahí los invito, lo pueden encontrar, también lo tenemos en nuestro canal de YouTube. La entrevista se hizo a Juan Francisco, ahí él habla un poquito acerca de este tema. Listo, tenemos más preguntas por acá. Juan Carlos nos pregunta, do you think quantum computing can completely replace classical computing? Can they work together?
Yes, absolutely. So quantum computing is good for specific things, but for many areas, classical computing is still much better.
Ok, la computación cuántica realmente puede abarcar muchísimas áreas, entonces sí es posible que pueda, digamos, abarcar muchas áreas pues en un futuro cercano.
And also there are what are known as hybrid algorithms, which break down a problem into parts that can be done really well on a classical computer and other parts that are for a quantum processing unit to do.
Ok, hay algunos algoritmos que funcionan de forma mixta, en los cuales uno puede romper el problema y atacarlo desde la parte clásica y otro desde la parte de la computación cuántica. Entonces sí pueden trabajar en conjunto.
Van a trabajar en conjunto. A eso vamos a llegar. Listo, vamos a leer una última pregunta de Sebastián Rodríguez. Dice, how many years do you expect the quantum computing arrays is standard form? Sorry.
So I think what this question is asking is how long will it take us to get to the full-scale fault-tolerant era?
Yes.
So that could be, well, there are different estimates. So companies are optimistic or pessimistic. I would say 10 to 15 years.
Ok. Tomás dice que pues realmente hay algunas compañías que son un poco más optimistas que otras para que la computación cuántica, digamos que llegue a un nivel estándar, pero puede ser entre 10, 15 años, de pronto un poco más.
Vamos a migrar definitivamente allá. Listo, sé que se quedan algunas preguntas en el chat. Tengan la certeza de que las vamos a ir respondiendo de manera escrita. Ahora en un rato nuestro equipo nos va a ayudar a respondérselas para que no se queden, digamos, con la incógnita. Yo le doy gracias a Tomás y a Oscar por haber hecho parte de este panel, por explicarnos un poco qué viene hacia un futuro que, según esta última respuesta, creo que no es tan futuro. Realmente creo que es un futuro ya muy cercano. 10 años implica que desde ya nos estemos preparando para esa era, o bueno, 15 años. Así que es uno de los casos en los que definitivamente el futuro es hoy y nos tenemos que empezar, digamos, a preparar. Es lo que he entendido un poco acerca pues de este cambio y esta era que viene. Les doy muchísimas gracias a todas las personas que se conectaron, tanto en YouTube como en LinkedIn. Ya por temas de tiempo, pues vamos a cerrar este espacio. Sin embargo, los invito a ver los videos que tenemos. También tenemos un video con Tomás en donde hicimos una entrevista hablando un poco también de este tema y de qué viene para la inteligencia artificial. Lo encuentran en nuestras redes sociales, en nuestro canal de YouTube también lo encuentran. Y nada, ya les doy en serio las gracias a Synertic también por unirse a este webinar y pues por supuesto a nuestros panelistas que hicieron una exposición muy clara también que nos abre un poquito la mente y el panorama a lo que va a pasar. Espero volverlos a ver en próximos webinars. Que tengan un feliz día.